Yeah, on this one.
Quick feedback on the quiz. Okay, so whenever this one pulls, it's a falling edge, and we all know that the capacitors can, whenever you have, so falling edge means what actually? Very quick question. So you have learned circuits, right? Circuits, and in circuits they tell you that capacitor can pass AC but block DC, right? And resistors pass DC and block. Wait.
Inductors?
Inductors passes DC and block AC, right? Because whenever AC is oscillating voltage, it will generate a magnetic field to up in the opposite direction of the to prevent that current from flowing in that direction. Okay. So this from another idea in the very practical circuit design. You know, that's the inductor, and you have a lot of circuits here. And they want to put an inductor here. Why?
I guess block the AC current from alternating to the negative voltage and pulling from the ground.
So what is this one providing?
0 volts.
Yeah? And you hope this one to be what?
Greater than 0 volts? Oh, that's
Steady 0 volts, right?
yeah.
And they place the inductor between the device ground pin and the real ground. Doesn't matter. You're thinking, hey, you're blocking the ground. Why do we do that? Is ground being affected?
No,
Why?
because
Because it's DC.
yeah.
Even though it's 0 volts, it's DC. Okay? So DC can comfortably pass that inductor, but any noises, you have all the other circuits sharing the common ground, but this is like a super noisy circuit, and there will be some noises getting into here, and this inductor will block it. So that's one application of that. You can see this from the microcontroller skateboard actually. There are a couple of inductors that's being used for this purpose. All right, come back to this one. So a floating edge is considered as a AC signal. Okay? It's changing. It's not steady signal. It's not DC. So it's a instantaneous AC. It's changing. So the AC will pass this guy, right? So that's why it's able to pull charges through it. It's passing the capacitors, it's pulling charges, and then whenever it goes up, it's trying to push it back, and there's no way it can go back. It's blocking it. So eventually it stores the charge across the capacitor. So that's how you are pulling charges through it and eventually store something over here. And what is that voltage? When you pulse it, it's going to be VDD minus VTHN. And when you push it, so you are basically adding another VDD here. So like a battery, plus minus, and this is ground. What's the voltage? Is that crystal clear? What about here? So that's just the filter. It's another filter. So it filters out any ripples, but keeps the DC component over there. And eventually you are getting what? So yeah, let's take a pause. If I don't have this guy, only connect capacitor to this oscillation, I might getting a filter. Is that a filter?
Yeah.
If there's a like oscillation here, right? And you directly connect that oscillation to a capacitor, is that a filter?
I guess yes.
What's the time delay? It's the filter, then what's the delay? So because whenever there's a filter, which means it creates a lot of time delay to make it not able to charge and discharge the cap. So eventually you are not passing all the AC oscillations, right? But what about this guy? Like, if it's just wire, we consider this as a ideal metal, right?
There's no power.
And there's no resistor to resist it. It's actually, it's infinite amount of current being dumped into that. If it's resistor 0, if you do a V over R, the current is infinite. So there's no time delay. But you adding this one, not just blocking it, but also this device will have some sort of resistor inside, and it's an RC circuit, there will be a time delay, right? And so it's a 0.7 RC. If this is huge, you can either make a R huge or you make a C huge to create a huge amount of delay in order to not be able to oscillate it. Here's 0, this is your oscillation, right? And there will be RC delay. If you don't have a huge resistor or huge capacitor, it will be able to do this. Okay? Remember we did a lab on that, right? I use the different sizes of the inverters to charge up the cap. Okay? But if you use big capacitors over here, and it will eventually become what?
Almost DC.
Almost DC. If you put an ocean here, ocean, not a bucket, ocean, and you are using a straw trying to put some liquid in the ocean, can you see ripples? So the shark on the other side of the ocean will feel it. Someone is dumping water in here. No ripples, right? No ripples. So you just need a huge bucket in here to make this happen. Yeah? That's the answer. So this is the answer. This is the answer. And there might be a little decrease from this, so you are expecting the DC to be stabilized at around 2 VDD minus what? 2 VTHN, because there's a drop over here as well, but being smoothed out, okay, eventually.
Oh, where's the 2 VDD coming from again?
Here. When it pushes, because previously it pulled. So it stores VD minus VTN over here, right? And the next cycle it pushes.
Okay.
So you're adding a VD here, so you measure, you have a multimeter to probe the red probe and black probe like this, right? So eventually you are detecting VD minus VTN and VD, so eventually 2 VD minus VTN.
Yeah.
Since you are,
So for I'm talking about for B, or even not B yet.
which one?
For point B.
Okay, yeah, because you have VDD, so this is VDD minus VTN over here. I mean for A, right? This is a lower voltage, this is a higher voltage.
Yeah.
And they will both pass, but the thing is this filters out the ripples, the oscillations. And eventually only the DC component can go through, but being dropped by another VTHN. So it's adding another VTHN to it. So eventually it won't exactly be that, I just estimate, okay? Eventually it will be a DC at the top of the oscillation, but won't get discharged or charged and discharged eventually. And the first time it's able to go up because it's an AC signal, it will be able to go up. But after that, it won't be able to discharge. So we'll have a higher starting point, and eventually we'll be able to go to the top because it's a higher starting point. So it's easier to charge up for this little distance over here, and but won't be able to discharge. Won't be able to discharge since the ocean is the ocean. Okay? And for the quiz, and also for the course project, one of the questions is, how do we lay out a capacitor? How do we lay out the capacitor? So the capacitor is, there are multiple ways to do it, okay? There are multiple ways to do it. For the TSMC technologies, there are metal-to-metal capacitors, since we know that this is poly 1, metal 2, right? So some of the process or the foundries will give you, for example, TSMC will give you MIM, this type of capacitors. It's a metal-to-metal capacitor, and for example, it may not be exactly like this, but similar, right? So drew a via here, and that's a via, and that's metal 1, that's metal 2. Alright, so metal to metal is 2 metal plates, and it's just looking at the overlapped area over here to form the cap. Does that make sense? So in your layout, you lay out the metal 1. Can you change the distance, the thickness of the capacitor? So capacitor equals what? C equals rho. No, sigma, right? Sigma. A T. Because larger area is larger capacitance.
Well, you could just
And
change,
shorter distance is larger. What's that?
you could just change the length, right? Maybe I should change the thickness, but you could change the length of the.
And because there's no way to check the thickness
Yeah.
defined by the process, right? So the thickness of the insulator is defined. So you can just change the area. So when you are doing the layout, when you're looking at the monitor of the screen, right? So the electric VLSI, the software, you are able to draw a capacitor by using a box, draw a box of one layer, and you draw another box of another layer. I have a lot of vias over here, a lot of vias over here, right? So you can make connections. And the effective area is only this overlapped area for the cap. So you look at the area of it, you can get an A, okay? And the precise, depending on which foundry and which precise, they'll let you know the thickness or the sigma here. That sigma? Epsilon? Epsilon probably. Epsilon. And they will let you know the parameters, and you can just plug in the area to calculate the capacitance, right? These are vias, metal 1, metal 2's vias. And for the quiz, if I'm asking you to draw a layout, not a sig diagram, but a layout similar to whatever we drew in electrical VLSI, it shouldn't be that difficult, right? So when you're drawing that layout, you just have these ones, and inverters. That's a gate. Alright, do this. That's an inverter, right? What is this?
It's a VDD.
Yeah, VDD sometimes you don't want it to be VDD, just let you guys know. So for general cases it's VDD, but what are these components? So what is this parts? What's the name of the part in the library?
Well, it's a well or a tap.
Unwell tap. And we just shorten unwell tap to VDD, okay? So for unwell type, if I have unwell like this, unwell type has all the vias and metal 1s, and the PMOS has unwell like this. Is this correct? No,
No.
they have to overlap.
Yeah.
Same unwell. That's why you are using the tab. The tab is typing the unwell of the PMOS. And if all of the unwell tabs are shorted to VDD, like the one next to it, also shorted to VDD. If not, then you want to do it in a different way. If, I'm just drawing this fast, okay? Is this correct?
Yeah. Well, they're connected, right? So B.
At least you need to short the VDD together. They are both VDDs, right?
Yeah.
What else?
Um,
They are both VDDs, and the unwell tabs and unwells are both shorted to VDDs. Why do you want a gap over here?
the body effect?
No, you don't want a gap. It's the same unwell.
Yeah. Okay.
So when you do the quiz, if they have the same unwell, you want to draw it. Same here. You got all the P-well tabs, and you want to draw a universal P-well to cover it. And there should be a gap in between. Keep in mind, these shouldn't overlap. And do you really have a P-well in your in your electric VLSIs, the C5 500 nanometer technology? Is there really P well?
No, it's just pieces.
It's just a P stub, it's just a wafer itself. But for the foundry, we still want to draw it. Okay, that's will be a lot better, or required sometimes. It's not reporting well errors. So the foundry knows that all these devices, tabs and devices are being placed in the P substrate without, any other things to cover it. So if there's another device next to it, okay, let's see if I can draw it. Another device next to it. And this device requires a separate well. Could you do a separate P well? Is that possible to create a separate P well? Why?
No, because they're in the same substrate.
It's the same wafer. If you break the wafer up, then that's a different chip. It's chip number 2. But do we need to? Probably not. Okay? So for PMOSes, if we need a different NWEL for that single PMOS, what should we do? N-tab to what? N-tab connect to where?
A separate in-law.
It won't be VDD anymore, right?
Yeah.
Okay, so it's somewhere else. I'll let you label it, okay? And then for this guy, would you like to draw a universal P NWEL like this?
No.
No, that's the whole point. Separate it. Do this. Do this. The well tab still belongs to that NWEL. However, this NWEL should be separated from the universal NWEL, which is shorted to VDD. So this is not shorted to VDD, so we don't want to short it. You don't want to connect it to it. And this one need a different connection. Where? To where? To the highest potential available on the circuit. It could be somewhere, okay? If the source, it's just shorted to the source. You are saying, hey, I don't have any signal from the source. I don't have any signal from the VDD. But this is not VDD, so it's fine. Right? It's not sourcing any current from the VDD. And then if you need to draw a capacitor, you just draw a capacitor over here. Okay, draw a capacitor. You just have all the components laid out over here, and you draw a capacitor. Okay, here's the vias. And make the connections. Okay, to whatever you want. So for however, we're not doing MIM. Okay, we're not doing metal to metal. So what we are going to use, what is available for C5, is actually poly to poly. So in that case, you have to label the metal layers. For this one, okay, I'm not doing metal 3. Okay, this is metal 1, this is metal 2, this is poly. There are actually 2 poly layers available. If you take a closer look at your electric VLSI library on the left hand side, you will be able to see that. There are 2 different poly layers, but only the poly 1 is being used as a gate. Poly 2 is somewhere else. You never used it, but it should be used for capacitors. So there's a poly 2 on the top and poly 1 at the bottom. That's P1, that's P2. So for the vias and connectors for P2 and P1, it should be both metal 1s. So it should be poly to metal 1 vias, but there are different vias. Poly 1 to metal 2 via will be different from poly 2 to metal 1 via. Of course. Obviously, right? There are different poly layers, there are different vias.
So
And they have a metal here, and they can connect to metal 2, metal 3, eventually connect to all the circuits, right? So this overlapped area will form a capacitor. And it's using that very thin dielectric material, which is a silicon dioxide, right, in the middle, as a dielectric material. Okay, so for here, when you are doing the layout, you just draw a capacitor next to it, which is fine. I don't care. So then you just label the metal layers and connect them with certain traces. Right? I won't be super picky on the labeling of the layers. for the metal traces, because there will be a lot of connections, right? A lot of connections, and you are trying to avoid short circuits within that little area. You probably don't have different color of pens with you, so I won't be super picky about that of the wiring. But if you can label that would be great. So I understand what you are doing. I can give the credit on that. Okay. Any questions on this?
This very quiz to me.
Yes. What's that?
So is it okay if we do the capacitor schematic symbol, or do we have to do the layout of the capacitor?
Just layout. Just hand draw layout. Just assuming that you are doing electric VSI. Okay, but hand draw it. Not see diagram.
And what are the layers of the capacitor? It's just
Poly 1, poly 2.
okay.
If you can label it, that'll be great. If you don't label, it's fine. I don't care. Just draw 2 boxes and overlap, and then 2 terminals and make the connection, certain connections, 2 places.
So would you rather? I'm guessing you'd rather just use the poly capacitor rather than the metal one.
I don't know if the metal ones are available for C5.
Okay.
It's a 40-year technology. It probably doesn't have metal to metal capacitors. You can form a capacitor by doing that. That of course, right? But the thing is, probably the parameters in between are not available. Any questions on this? The size of the circuit is pretty small, so it's doable. It's just a circuit we covered on Wednesday, right? On Wednesday. Just this circuit, would you be able to lay it out? Wait, just this guy. Just 2 NMOS transistors, 2 caps, and 1 inverter, one inverter, and another inverter over here. That's it.
By hand?
Yeah.
It'd be
With do we need to do cross sections of everything?
No, just a top view, just like this.
oh,
See how long it took me to draw an inverter like this?
Okay.
The box, connections, taps. That's 1 inverter,
yes, it'd be
and you only have like a 1, 2, 3 inverters and 2 NMOSes.
Okay.
I want to show this picture because these are just 2 NMOSes, but nothing else.